Alright, so if we have a finite dimensional linear space and t is an operator in V, that means that the domain and codomain are both V. It maps from the inputs to the same set of inputs. So the outputs are the set of outputs, potential outputs is the set of all inputs. Then the following are equivalent. T is invertible, T is 1-1, T is surjective. What this means is that if you know that it's invertible, you automatically get 1-1 and onto for free. Surjective is the same as onto. And we already knew that. But if you have 1-1, you also automatically get injective or invertible and surjective or onto for free. And if it's onto, you get 1-1 and invertible for free. So this actually says a bit more than what we've seen before. And the way I'm going to prove that is I'm going to prove that invertible implies 1-1, and then I'm going to prove that 1-1 implies onto, and then I'm going to prove that onto implies invertible. And what does that mean? That means if you have that's invertible, well, this means that if it's invertible, it's 1-1. So if you know it's invertible, you know it's 1-1, but if you know it's 1-1, you know it's onto. Similarly, if you know it's 1-1, you know 1-1 means it's onto means it's invertible, so you get all three. If it's invertible, or if it's onto, that means that you know that it's onto means it's invertible. If it's invertible, it's 1-1. So you get all three. And the way I'm going to prove this is relatively easy. So if I know it's invertible, I can use this. It's invertible if and only it's 1-1 and onto. So I'm just going to use, if it's invertible, it's 1-1. So I'm not going to use the full power of this, but fine. So this is by theorem 147. Great. If it's 1-1, it's onto. The key thing here is that it maps V to itself. And so I'm going to use theorem 139. Which says, if you have a map T going from V to V in our case, if V is finite dimensional, then the dimension of V is equal to the dimension of the null space, the kernel, plus the dimension of the image. So that's what I'm going to use to prove this. So, by theorem 139, the dimension of the null space, or the kernel of T, plus the dimension of the image of T is equal to the dimension of the set of inputs. In other words, the dimension of V. But by theorem 146, if it's 1-1, that means the kernel is 0. So 1-1 implies the kernel T equals 0 by 146. So this dimension is 0 plus the dimension of the image. So in other words, what I know is that the dimension of the image is equal to the dimension of the entire thing V. So that means that the image of T equals V because they have the same dimension, so they're going to be isomorphic. And since the image of T is a subset of V, we have that the image of T equals V, so it's onto. That's what onto means. It means that the image is everything. So finally, for onto, so we're done with that. So if it's 1-1, we automatically get that's onto. So let's assume that's onto. If it's onto, we're going to prove that it's invertible. And what I'm going to use here is we're going to use theorem 147, which says that if it's 1-1 and onto, it's invertible. But I'm first going to start with 139, which I just used, which means it's dimension kernel T plus dimension of the image of T equals dimension of V. And if I know it's onto, that means that these two things are equal. So dimension of the kernel of T plus, if these two things are equal, I'll just replace this with dimension of V. Dimension of V. In other words, the dimension of the kernel equals 0. The only thing with dimension 0 is the thing that only contains the 0 vector. So the kernel of t is equal to 0. So, by 146, t is 1 to 1. I'm using all the same stuff again and again in different orders. So what do I know? I know if it's onto, that means I get 1 to 1. So 1 to 1 and onto. So it's invertible by 147. And that's what I wanted. I want onto implies invertible. So how did I do this? If it's invertible, it's 1 to 1 and onto, but all I need is 1 to 1. Great. If it's 1 to 1, I'm going to get this onto basically by the fundamental theorem of linear algebra here. Get the dimension of the image equals dimension of v, so they have to be equal, which means that it's onto. And then if it's onto, I'm going to prove this 1 to 1 first. And I can prove it's 1 to 1 by using the fundamental theorem of linear algebra to show that the dimension of the kernel has to equal 0. Dimension of the kernel equals 0. That means the kernel has to be 0. Kernel equals 0 if only if it's 1 to 1. If it's 1 to 1 and it's onto, which I'm assuming, then it's invertible by 147. So these three things are all the same as long as you're mapping v to itself. We're done.